Okay, so as Katie said, I'm going to be talking a little bit about zircon today. So zircon's a mineral I've been interested in for a little while now. I've just recently finished my PhD at Imperial College. My PhD, so Jamie's already shown you this slide, but this is, you're going to get sick of this. If anyone comes to another talk I do in the future, you'll definitely see this. I'm proud of this, and rightly so. This is perhaps quite a good metaphor for the area I'm trying to forge for myself in academia. So looking at magmas and interested in all the processes by which magmas have generated and evolved and crystallized, but also their implications for the formation of porphyry copper deposits. And we've heard lots of talks about how that magmas are very important in generating the fertility, that generating the actual deposit themselves. So that's something I've been looking at. So in my PhD, it was fully funded by Rio Tinto. I was interested in essentially the processes by which magmas are generated down here in the lower crust of the moho, the upper mantle, and the processes by which, as they rise closer to the surface, they fractionate, and eventually in the ore-forming environment up here, how igneous processes can control that. And the reason in particular for doing this was that I was interested in whether the divergent processes that govern whether you get a porphyry deposit or whether you get just a normal magmatic system, whether they have any telltale geochemical signatures in them, and whether those signatures in the magmas are then picked up in any minerals or in the whole rock when it eventually crystallizes. And then ultimately, if you can use any signatures that are unique or distinctive of porphyry copper deposits, use them as for exploration. So that's how Rio Tinto were involved. So many of you know this. I'll run through this very briefly, but zircon's a really great mineral for an igneous geochemist, particularly one who works in porphyry deposits. And there's a variety of reasons here. I've put some of my favorites. Firstly, it's extremely resistive to high temperature diffusive reequilibration. So once you form a zircon, usually the signature that's recorded will stay there. And even if you completely frazzle the thing with acid, you look at a rock that's very strong advanced argillic alteration, you may still have zircons in there with useful information, even if the rock chemistry isn't changed completely. We've seen a few talks about how they're useful for dating, so that's something we all know. They occur in lots of igneous and felsic rocks, and although they're not super abundant, you can separate them quite easily. They have a lot of trace element substitutions, so there's a lot of things to analyze. And in particular, some of those trace elements that substitute into zircon are sensitive to some parameters that we're interested in from a fertility perspective. So temperature is very important, but also FO2. We know that oxidation state is extremely important in the evolution of magmas which go on to form porphyry systems. So in the talk today, I'm going to be focusing on particularly some rare earths, europium and cerium, and their partitioning into zircon and its relationship to FO2, or not. So just a brief primer about rare earths and how they partition. Essentially, if you're a rare earth element and you're aspiring to be incorporated into a zircon crystal, you want to make yourself about the same size and charge as zirconium 4+. So there's a couple substitution for rare earths here, and so you can substitute in, and you want to be around this size, 0.84 angstroms. So you can see that something like lanthanum, which has a very large ionic radius, this is not going to be going into zircon at all. Firstly, it's much too big, and also it's slightly the wrong charge as well. But as you can see, as these ions get smaller, the charge size shrinks. So by the time you get to lutetium, can't even read that, 0.97 something. That's much closer fit for zirconium. And so in zircon, what we tend to find is that you have an increase in the concentration of rare earth elements as you go from the light end to the heavy. So the heavies are more compatible in general. And obviously most of the rare earths exist in the 3+ oxidation state. Now there are a couple of notable exceptions here. So both cerium and europium in natural magmas can exist in other oxidation states. Europium is 2+ and cerium is 4+. So europium 2+, this is rubbish for getting into zircon. It's way too big. The charge is, it's really different. So europium 2+ really incompatible in zircon. And for that reason, because there is usually the ratio of europium 2+ and 3+ and melts is that you have some of both in most terrestrial magmas. So you end up with a negative europium anomaly typically in zircon. Now on the other hand, cerium 4+ is not only the right charge but the right size. And so that's a dead ringer for zirconium. It'll just substitute straight in. So the partitioning behavior of cerium 4+, it's incredibly compatible in zircon. And even if you have only a vanishingly small amount of cerium 4+ in the melt, and we do, it's if you look at the ratio of cerium 4 to total cerium in sort of 700 degrees and FMQ plus 2, it's something like 0.0016, something like that. So vanishingly small amounts of cerium 4+. Nonetheless, you end up with a positive cerium anomaly because cerium 4+ is just so compatible in zircon. So this is a typical sort of zircon pattern that you might expect to find. And this has been demonstrated experimentally by one of our former colleagues at the Natural History Museum, Anthony Burnham. He did his PhD looking at zircons. He grew them in the laboratory at different FO2s and demonstrated that under very reducing conditions, as you might expect, you have a very neutral, flat, you don't have a cerium anomaly essentially because there's really just no cerium 4+ around. But you also have a very deep negative europium anomaly. But under very oxidized conditions where there is some cerium 4+, and where most of the europium is europium 3+, you end up with a neutral europium anomaly and a very positive cerium anomaly. So it has been demonstrated experimentally that both europium and cerium under normal conditions are sensitive to redox. So if you want to quantify this, then this is the way that people mostly go about quantifying europium. It's europium over europium star, where europium star is how much europium we would have if it was just behaving normally, intermediate between samarium and gadolinium. And this is the way you can calculate that. Similarly with cerium. And typically we have cerium over cerium star values greater than 1, and europium star values of less than 1. The problem with this is that, well, as far as cerium is concerned, lanthanum and praseodymium, very difficult to measure in zircon. In fact, actually, you're most of the time below detection limit. So you actually can't measure cerium over cerium star the way that I've just showed you. So we've come up with an alternative way that you can do it, where this is just essentially rearranging this sort of geometric mean, where you use neodymium and samarium instead, and sort of pin cerium star against those two, because these two are usually, you can normally measure these. And then you just essentially rearrange this equation for cerium star, and then cerium over cerium star. So that's another way you can get around it. But analyzing, quantifying the magnitude of that cerium anomaly is extremely difficult. And there are other ways you can estimate the cerium anomaly. One is to actually estimate the ratio of cerium 4+ and cerium 3+ in a zircon. And this is exemplified by Julian Ballard, a paper a few years ago now, where he estimated the cerium 4, cerium 3 ratio by using this equation here. So there are a few parameters that you need to constrain in order to do this. You need to know how much cerium's in the zircon. That's fine, we can do that. Cerium in the melt is a bit more difficult. Maybe you can use the whole rock geochemistry as a proxy. And then also these two parameters here, the partition coefficients for cerium 4 and cerium 3. And you can estimate these by sort of interpolating between the partition coefficients for the other 3+ cations and the other 4+ cations. You end up with some values here. So that's another way you can get this ratio of cerium 4, cerium 3, essentially a proxy for redox in zircon. So how this relates to porphyry deposits, as we've seen this before, but this is from our paper that's been published quite recently. When you compile all the data from sort of barren sources and from the literature, barren and fertile magmas, so those associated with porphyry deposits and those which are not, you see that for europium star and cerium over cerium star, there's not a perfect separation between them, but generally, zircons associated with porphyry deposits have higher values for both of these. So this is, and there have been several papers on this recently where you can begin to use this as a criterion from which to distinguish zircons from barren and fertile systems. Now, when you actually look at this in the field, it gets even more intriguing. So here this is work from, again, Ballard, in fact, from the Fortuna complex near Chuquicamata in Chile. You can see that in the period leading up to mineralization, this ratio of cerium 4, cerium 3, so redox by proxy, increases gradually in this series of intrusions, leading up to the period of mineralization when it reaches its zenith. So perhaps we're seeing, over the course of maybe sort of 10 million years, a progressive oxidation in progressive intrusions leading up to the point where mineralization takes place, and then they are at their most oxidized. So it seems like zircon or these particular parameters provide a good measure of fertility, a good measure of redox, and they tell us something about the magma. I'm going to essentially spend the rest of my time explaining why I don't think, actually, that zircon is an especially robust measure of redox in terms of these parameters. Although I still think, as I've demonstrated here, I still think it has potential as an indicator of fertility. I just don't think these parameters are reflecting redox in a meaningful sense in natural systems. So I'll focus on europium. The reason why I don't think europium is necessarily so good as a measure of redox is europium can be affected by all other different phases. So I plotted here from the literature partition coefficients for the rare earth elements for various sort of common igneous phases. We have pelagic layers at the bottom here, hornblende, and then two different titanite experimentally derived partition coefficients. And you'll see all of these minerals here have a preference, so at a fixed FO2, which is reasonable given what we know the FO2 conditions are like in arc magmas. At a fixed FO2, you can see that europium is either more or less compatible than its neighboring rare earth elements in zircon. So for pelagic layers, europium is way more compatible because 2+, if you have europium 2+, sorry, this is rare earths into these minerals, sorry. 2+ europium will substitute into pelagic layers quite easily. Whereas for hornblende and for titanite, actually europium is less compatible. So if I crystallize any of these phases from a magma, then the residual melt is going to be potentially enriched or depleted in europium with respect to these neighboring elements. So it imparts a signature, a europium anomaly on the residual melt. So to give the example of titanite, if you crystallize some titanite, you're removing more europium from the melt with respect to samarium and gadolinium. You're removing more samarium and gadolinium with respect to europium. So you're causing a positive europium anomaly to be formed in that residual melt. And any of these signatures that get formed in residual melts can be picked up by co-crystallizing or subsequently crystallizing phases, such as zircon. So it's possible that by crystallizing titanite, you're increasing the europium anomaly of the melt, and that could have an impact on the europium anomaly of the zircon. So I went to Oyu Tolgoi and collected some samples. So I'll just give you a very brief bit of background about Oyu Tolgoi because it's not really been talked about so much. So it's a string of porphyry deposits in the South Gobi Desert. It's one of the highest concentrations of copper and gold from Paleozoic rocks. These are all sort of late Devonian porphyry intrusions. So there are a few Paleozoic porphyries that are as big or as extensive as Oyu Tolgoi. There's a series of deposits which all have different metal tenors, metal associations, but also different sizes and grades. So here in the sort of northern part of this string of deposits here, you have the Hugo Dummit deposits, and they're extremely high grade and high tonnage. Further to the south here, there's the Heruga deposits, which are more modest grade, more modest contained copper. But they all have similarities. They're all approximately the same age. They're all hosted in the same rocks. They all have the same sort of associated quartz monzondiorite intrusions. They've all been buried by this later thrusting rocks over the top of them, which have covered them, and they're all cross-cut by these later dikes. So they're clearly part of the same broader system, and yet we have quite a divergence in terms of the size and grade that's between these two deposits, which is quite intriguing. So one of the things we can do is we can look at zircons from the intrusions in the Hugo North and Hugo Dummit South, and look at them Heruga and see if there are any differences. Maybe those differences reflect some process that explains why they're such different sizes and grades. So I analysed zircons from both Heruga and Hugo Dummit, and here's something that struck me straight away was there appears to be a bit of a bimodality in the data. When you just consider the geochemistry and don't look at the textures, there's a bimodality. And this is most obvious in tantalum. So you can see there are two peaks in tantalum frequency here, one about sort of 0.15, something like that, and one about 0.4. And there's a real paucity of zircon compositions here, about 0.2. So, and you can see this here on a plot of tantalum versus niobium. You can see there's even a different tantalum-niobium ratio for these two different groups here. So we can draw a line through here and primitively sort of call these ones here the low tantalum zircons and call these ones the high tantalum zircons. That's the nomenclature I'm going to use to describe these zircons in terms of low tantalum and high tantalum. And I'll describe them like that going forward, so it's worth bearing in mind. Just a point to make here, you can see that low tantalum zircons occur at both Heruga and Hugo Dummit in approximately equal proportions. So there's no fundamental difference, it seems, between the zircons at Heruga and Hugo Dummit. So when you actually look at these minerals and look at the textures, the zoning, you start to see some consistency in where these different types of zircon are found. So in general, the cores of zircons tend to be quite boring. They're like, if you've ever analyzed zircons, these are like the zircons you've already analyzed, okay? So europium star, about 0.4, that's quite typical. Ytterbium gadolinium of 38, so that's a measure of the middle rare earth depletion with respect to heavy rare earths. And tantalum concentration is about 0.4. They're quite typical for zircon. And they're in the cores here. But the low tantalum zircons, they tend to be found in the rims here, and they have much, much higher europium star and much higher ytterbium gadolinium ratios. This is really intriguing. There's a really strong disconnect between the cores and the rims in the zircons at Oyu Tolgoi. So I put up some other parameters here. So the rims, which have high europium anomalies, really high cerium 4, cerium 3 values, compared to these sort of more boring plain cores. So immediately this is interesting. We've got these parameters here that we think are associated with redox, associated with fertility. We're finding them in a large Paleozoic porphyry system, but we're only finding them in the cores. Maybe something's switched in this sort of dissolution boundary here. Maybe some process has changed. Maybe there's been some oxidation or something like that. But I also noticed it's extremely common to find titanite, very small titanite inclusions, in the rims of these zircons. So titanite and zircon are co-crystallizing, and the titanites are being included in zircon. Now, you do not find titanites in the cores unless those cores also have these very characteristic geochemistry. So wherever you find these little titanite inclusions, you also find elevated values of these two parameters and much lower tantalum, obviously, and also a lower tantalum-niobium ratio. Now, just a note here that we've got some values for europium star, which are 1.5. So that's a positive europium anomaly in zircon. Now, it is not possible to generate a positive europium anomaly in zircon just by redox alone. You could say this is super redox, super oxidized, but that cannot be the case, because if in the most oxidized system you could imagine, all the europium is 3+. All that means is that europium just behaves intermediately between samarium and gadolinium. So you wouldn't get any europium anomaly at all. Oxidation just gets you to europium star of 1. Anything above that has to indicate that the melts from which that crystallized were themselves already enriched in europium. They had a positive europium anomaly. That's something to bear in mind. So when we look at these actual rare earth patterns, I've split these up in terms of the cores, which are high tantalum, and the low tantalum rims here. As I say, the cores you've probably seen this sort of zircon pattern before. This is very typical. They tend to have this slight sort of concave downwards, sort of a slight depletion in the heavy rare earths, sort of a curve, some europium anomalies, negative europium anomalies, and positive cerium anomalies. This is sort of zircon 101 in terms of rare earth chemistry. These rims are quite unusual. These rare earth patterns are a lot flatter. They don't show this sort of curve pattern that you get in the cores. Also, you'll notice, as I said, the europium anomalies are essentially non-existent. The cerium anomalies between these are not really that different. So cerium star, as we calculated it, they're pretty much the same, which is a bit weird, because you'd expect that it would vary with respect to these other parameters as well, if cerium over cerium star is following redox. So these are rather uncommon rare earth patterns, and they require an explanation. So what I thought I'd do is maybe we can do this by titanite. So we have depleted middle rare earths here with respect to the cores. So maybe that depleted middle rare earth is because titanite likes to take in middle rare earths more than it takes in the heavies. Maybe we can do that, and maybe that can explain the europium anomalies as well. So I took the whole rock data. I took the average quartz monzodiorite, the rock from where these zircons came. I took that composition, and I did a very simple Rayleigh fractionation model where I took incrementally small amounts of titanite from that bulk rock and produced a series of hypothetical melts. So we're talking 0.2, 0.3% titanite crystallization, produced a series of hypothetical melts. And it produced a pattern that perhaps you might expect the middle rare earths become progressively, well, all the rare earths become depleted, but especially the middle rare earths. So the ytterbium gadolinium ratio increases. Also, you'll notice that these get a pretty sizable positive europium anomaly in these residual melts. And significantly, we didn't really need to use an awful lot of titanite in order to do this. You're only dealing with sort of 0.4% titanite crystallization in order to generate a very significant effect on the residual melt. So think of any sort of I-type intermediate rock that you've ever looked at in thin section, and think how much titanite there is in there. 0.4, probably not such a bad shout, and it has a very significant effect on residual melts. So if this is happening, if this process of titanite crystallization is occurring in situ in the shallow crust, so we're not fractionating titanite, we're not removing it, we won't see that effect in the whole rock geochemistry. This can have a very significant effect on the residual melt, and that has an impact on the other crystals that are co-crystallizing with titanite. So what we can do now is take these hypothetical melts, apply a zircon partition coefficient to them, and calculate what's the zircon in equilibrium with this melt and with this melt here. That was the next thing we did. We can compare those to what we saw at Oyu-Tolgoi. So these are the natural samples from OT. This is the cores with no titanite, and here are the rims with titanite. So when I calculate the zircon that's in equilibrium with the bulk rock, just our starting model composition, I find that it's really closely similar to the rare earth pattern for the cores, the sort of boring cores. So it seems like the cores of our zircons are in equilibrium with the bulk rock, which is perhaps what we would expect. Now, if I take our hypothetical melts and say 0.2% titanite fractionation, so a very small amount of titanite, and see what zircon's in equilibrium with that, it's incredibly similar to the, you might have missed that, hold on, very, very similar to the natural samples here. So we actually have it's difficult to almost discern these on the graph. The model is really closely replicating what we're seeing in the natural systems. So 0.2% titanite crystallization is able to replicate the zircon patterns that we see in the rims of those zircons. There's only a very small amount there. And this is a slide that Jamie showed yesterday. We can plot this up in multivariate space, essentially. We've got europium star here on the bottom, and then ytterbium gadolinium. This is a measure of the inflection in the rare earth patterns. So these are the natural samples here. The black circles are the rims with titanite. The white diamonds are the sort of boring cores. I've overlaid at the top over here just these are Alan Wainwright's data. He also did some zircon geochemistry at Oyu-Tolgoi. And most of his, he's got mostly the sort of high tantalum cores. Some of these low tantalum rims. And when I put my model over the top of this, you'll see that it's a pretty close match for that pattern you see there. And again, you're reaching a positive europium anomaly in zircon after only sort of 0.34% titanite crystallization. So europium anomalies, what about pelagic layers? This is something that people often talk about when they talk about europium anomalies. We don't have many europium anomalies in rocks associated with porphyry systems. This is typically suggested to be because pelagic layers is suppressed, so we don't remove a lot of europium as a result of our pelagic layers fractionation. So what we can do is if we know that titanite is going to cause a positive europium anomaly and pelagic layers will cause a negative europium anomaly, we can say in our melts, so these are melts now, what is the sweet ratio of titanite and pelagic layers, which will cause an initial europium star flat, so 1, what will cause it to be stable? And as you can see here, that if you have 99.69% pelagic layers crystallizing and only 0.31% titanite crystallizing, the effects of the pelagic layers are entirely negated by the crystallization of titanite. You end up with a completely flat europium anomaly for no matter how much crystallization you do of those things, basically. So in other words, although pelagic layers does have a very strong effect on melt europium anomalies, if titanite's also crystallizing, then you can just crystallize nearly as much pelagic layers as you want, and still you're not going to end up with this strong depletion that you see in the sort of 100% pelagic layers model. So that's europium. I'm going to talk now about cerium-4, cerium-3. I think this is also controlled by titanite crystallization. I won't go into this in too much detail, but here's Julian Ballard's equation again. And what I've done is I've plotted this, I've calculated this value, cerium-4,3, and plotted it versus the different parameters that are used in its calculation, just to show which ones are actually having the strongest control on this parameter. So you can see that of all these parameters, essentially, it's this one here, the partition coefficient of cerium-3+. Essentially, if you want to get this number correct, you need to have a very good handle on what the partitioning of cerium-3+ is into zircon, because you can see that it changes over several orders of magnitude. Okay, so how is this parameter actually calculated? So the way, as I said before, I'll go into it slightly more detail. You calculate the partition coefficients for the other 3+ cations, and you say, well, cerium should be somewhere here in between lanthanum and neodymium or something like that. But obviously you don't know what the partition coefficients are in a natural system, so the way that Ballard goes about this is you can Essentially, I've taken gadolinium here as an example that's not redox sensitive. You take the concentration in the zircon and divide it by the whole rock, and you could do that for all the rare earths. You end up with a nice pattern here. This is the sort of lattice strain parameter, and then you can interpolate cerium 3+. The problem is, if you've studied zircons, you'll know that for one given rock, I'll have zircons with a huge range of, say, gadolinium concentration. So this value here will vary sort of a couple, 3 orders of magnitude maybe. And I'm dividing all of those very different values by the same whole rock gadolinium concentration. So what I actually end up with is an enormous range of D values for any of the rare earths, which also means an enormous range of cerium 3+ values as well. And when you compare the values that you get, you calculate, and you compare them to sort of experimentally derived partition coefficients, you can see these partition coefficients, as temperature decreases, the partitioning of gadolinium, it becomes more compatible in zircon. And then these are mine here, just a different trend going off in a different direction. So the point I'm making here is that I don't think this method here is a very good way of estimating the partition coefficient for these rare earths. And because of that, it's a really lousy way of estimating the D cerium 3+. And because it's a lousy way of measuring the D cerium 3+, it's a lousy way of measuring cerium 4 over cerium 3 in zircon. You end up with an underestimate in D rare earths, and then you end up with the wrong sort of cerium 3+ value. So I think this trend that we've got here, this is not actually, you might think that this is increasing, becoming more oxidized as you go from here to here. Here are the rims, the sort of interesting rims that we've got. These are not more oxidized in my submission. These are just simply the effect of more extensive titanite fractionation, and not necessarily related to changes in redox. So just briefly about cerium and neodymium, this is another parameter that's another way that we can sort of go about estimating the cerium anomaly in zircon. I plotted these up last night after I've had a couple of beers, so don't grill me too much on this information. But here again, here are my data. So the low tantalum rims and then the high tantalum sort of cores here. So there's a couple of things you can see going on here. Firstly, we've got a general trend in this direction, even in the cores, in the high tantalum cores. But then you've got a divergence in this direction from the low tantalum zircons. So I can overlay, I can take my model again, retwist it so that I'm using hornblende instead of titanite. When I plot that up, I can see that for actually quite large amounts of hornblende crystallization, you can sort of replicate this trend that you see in these two particular parameters here. Okay, 80% hornblende crystallization, that's a bit silly. But depending on which particular partition coefficients you use, you can change this. Essentially, it's not changing the magnitude or the direction, it's changing the magnitude. So that's hornblende. It can explain it. So hornblende can cause changes in hornblende fractionation, can cause changes in cerium over neodymium. What about titanite? Well, it does the same thing, but it just does it a lot better. You need much less titanite, and it'll push you in this direction as well. So you'll get higher ytterbium gadolinium and higher cerium over neodymium. So I think that even something like cerium over neodymium is not measuring redox. It's just simply measuring the magnitude of titanite fractionation. So very briefly, because I'm running out of time, this is extremely important in porphyry systems. You find titanite, if you've got unaltered rocks, you find titanite everywhere. Here's some data from Yarrington. You see titanite concentrations, 3%, very, very high. In all these porphyry systems here, we also found it, or it was inferred to be there. So titanite is extremely important in the petrogenesis of porphyry rocks, and it has strong potential to impact on zircon chemistry. So I'm sort of run out of time. Here's my conclusions. I think I'll finish there, and I'm happy to field any questions if you've got any. Thank you.
That's great. Thank you very much. I think we've got time for a couple of quick questions.
So allanite's another very common mineral in these sort of I-type magmas. So have you considered the effect of allanite crystallization on?
Yeah, I mean, so allanite. There's plenty of other things that could also have an impact on this. Yes, no, I haven't considered allanite as the answer to your question. But the model we have is very easy to recast that for other minerals, and they would presumably have other divergent properties, and so. I think that's a way that we can think about zircon chemistry, is rather than these particular parameters. What's been crystallizing anyway. Yeah.
Especially for your light rare earths, allanite would be particularly effective at removing those, so it might have quite a strong effect, particularly when you're looking at your cerium.
Cerium anomalies, yeah. It wouldn't presumably affect the ratio of cerium so much to well, maybe it would. As I say, I don't know. I've not looked at that.
So when you plot up your zircons and you have barren and fertile fields, they're now barren and fertile in terms of titanite rather than copper
Yeah.
fertility.
If you're looking for titanite, then, you know.
Well done. But is titanite and these, you know, higher contents that you're seeing in the systems that you've tagged as fertile, is titanite an indicator for copper fertility? And if so, how and why?
Well, yes, in some senses. I mean, as I say, titanite is very common in porphyry systems. It is an indicator itself, ironically, of oxidized magmas. So you find titanite in more oxidized systems, and you find it in sort of hydrous, intermediate, metaluminous rocks. I mean, these are the type of magmas that we're interested in from porphyry systems. But you obviously don't just find titanite in porphyry systems. You get it elsewhere as well. So one of the questions that I'm interested in is why are these signatures so prevalent in porphyry systems that have titanite, and not so much in barren systems that have titanite, for example. So that's something that I don't think I've really been able to answer yet, but something I'd like to work on.
Thank you very much.